You'd think a heavier atom would be a bigger atom, right? I mean, more protons, more electrons. It just seems like it should be bigger. Well, in the wonderfully weird world of chemistry, what seems like common sense isn't always the case. Today, we're going to dive into the fascinating and kind of counterintuitive rules that actually decide just how big an atom is.
Okay, so let's get right to the heart of the puzzle that trips so many people up. Here it is. Nitrogen is heavier than boron. It's got more stuff in it. So, why on earth is it actually smaller? Yep, you heard that right. To figure this out, we have to stop thinking about weight and start looking at the powerful invisible forces that are constantly at war inside the atom itself. So here's our game plan for cracking this case. We're going to start with something called the invisible electron shield. Then we'll look at the incredible pull of the nucleus. Those two clues will help us understand the left-to-right squeeze, and then we'll see what happens when you start adding new layers. By the end, we'll wrap it all up with two golden rules that'll make you an expert. All right, first stop, the invisible electron shield. This is our first major clue, and it's all about how some electrons in an atom are basically playing defense for their teammates on the outside. Okay, take a look at these diagrams. You've got the positive nucleus in the center, right? And it's doing its best to pull in all those negative electrons. But notice how the electrons are organized into layers, or what chemists call shells. The nucleus is pulling on the electrons in that outermost shell for sure, but it's not pulling nearly as hard as it could be. Something is getting in the way.
And that something is called electron shielding. It's pretty much what it sounds like. The electrons on the inner shells form a sort of shield of negative charge. This shield partly cancels out the positive pull from the nucleus. So the electrons on the outside, they only end up feeling a fraction of the nucleus's true power.
Let's make this real with some numbers. Take boron. Its nucleus has a +5 charge, but those two inner electrons create a shield. So, what do the outer electrons actually feel? Not a +5 pull, but an effective charge of about +3.
Now, let's slide over one spot to carbon. It's got a stronger nucleus, a +6 charge, but it has the same two shielding electrons on the inside. So its outer electrons feel a stronger pull, an effective charge of +4.
And you see the pattern here. With nitrogen, its +7 nucleus is pulling against that same two-electron shield, which means its outer electrons feel an even stronger effective pull of +5. This increasing felt charge is the first huge piece of our puzzle. So we know the felt charge gets stronger as we go from boron to nitrogen, but how does that actually affect the size? Well, that brings us to our second clue, and it's all about the basic physics of attraction.
To make this super clear, let's forget about atoms for a second and think about magnets, or in this case, these charged spheres. The way the positive nucleus pulls on the negative electrons works a lot like the pull between these spheres. And the rule is dead simple. The bigger the charge, the stronger the pull. I mean, look at it. A +3 pulling on a -3? Sure, that's a decent pull. But a +5 pulling on a -5? Whoa, that is a way stronger attraction. They get yanked together much more forcefully. Okay, time for the big reveal. We've got our two clues, the felt charge and the fact that a stronger charge means a stronger pull. Let's put them together and solve this mystery. So, let's go back to our original question. We've got boron, with its outer electrons feeling a +3 pull, and we've got nitrogen, whose outer electrons feel a much stronger +5 pull. So, based on that, which one do you think is bigger? Here they are side by side. They both have two electron shells. And remember, nitrogen is the heavier one, with more protons and electrons. Every instinct you have might be telling you it has to be the bigger one, but chemistry loves a good plot twist.
And there it is. Despite being heavier, nitrogen is the smaller atom. This is the whole reason we started this journey, this completely backwards fact. But now, we actually have the tools to understand exactly why it happens. So here's how it breaks down. Both atoms have the same number of shells, 2, and the inner shield is identical. The only real difference is that nitrogen's nucleus has that stronger +5 felt charge, and that stronger pull acts like a superpowered vacuum, sucking that outer electron shell in tighter, literally squeezing the atom and making it smaller.
Okay, that takes care of moving side to side on the periodic table. But what about when we move up and down? This brings us to our second mystery. Now, check out these 3 atoms. They all belong in the same column or group on the periodic table.
And right away, you can see a really obvious difference in how they're built. If we break them down, you'll see they all have 8 electrons in their outermost shell. So that's not the difference. The key difference is the total number of shells. Atom C has 2, B has 3, and look at A. It's got a whopping 4 energy levels. And you know what? That's really the whole story here. This trend is much more straightforward. As you go down a column, every element you hit just adds a whole new layer of electrons. It's like putting on another coat in the winter. You're just going to get bigger. This effect of adding a new shell is so huge, it completely outweighs everything else. So we've gone through the electron shield, the nucleus's pull, the squeeze, and the layers. Let's boil all of that down into 2 simple, powerful rules you can use to figure out atomic size anytime.
Here they are. Rule number 1. As you move from left to right across the periodic table, atoms get smaller. That's because of that increasing nuclear squeeze. Rule number 2, as you move from top to bottom down a column, atoms get bigger. That's just because you keep adding on new layers. That's it. That's the whole game right there.
And now, it's your turn to put this into practice. Find phosphorus, antimony, and nitrogen on a periodic table. I'll give you a hint, they're all in the same column. Based on what you now know, can you put them in order from the smallest to the largest? It's a fantastic way to see for yourself how these 2 simple rules can unlock the secrets of the entire table.